Yeah, so Ex and H, remember, is the maximum number of edges in a graph on n vertices, which doesn't have any copies of H. Meaning it doesn't have like a subgraph isomorphic to H. So far, we determined this quantity when H is a complete graph. Over the next few classes, so today, next time, and a little bit maybe of the next lecture, depending on how things go, we're going to look at the more general question of what is this like extremal number of H as a function of n for a more general H. Yeah, so a lot of the things we did like last time in the last two classes involving Turan's theorem, like, we really, it might not be clear, to you right now, but we really used a lot of properties of complete graphs. And in some sense, when you deal with a more general graph H, you have less stuff, you have less understanding about the structure of H, so there's less that you can use. And kind of as a result of that, the results that you get are a little bit less precise, but we're going to get kind of asymptotic approximate results in some sense. Okay, but let's start thinking about this. So, this is yeah, so this is kind of related to what I just said. So if we were trying to get an exact formula for every graph H and every n, nobody knows how to do that, right? It's far too complicated. But our hope is that we can, for most graphs H, we can get like a pretty good idea of like the general growth rate of Ex and H as n goes to infinity. So we want to kind of determine, so our goal is to determine Ex and H asymptotically, and we're going to be able to do this as long as H is not bipartite. But we'll see the issue with bipartite graphs in a second. And when I say asymptotically, you should think of like, remember from the first assignment, you had Stirling's approximation, for example, which said like, as the limit goes to infinity, then, n factorial divided by whatever it was goes to 1. We want a sort of expression for this thing, which is not exact, but it like the ratio goes to 1 as n goes to infinity. Okay. Any questions about that? Is the goal clear? I know that. Well, we're not going to have to. That's the really nice thing about this, that, yeah, we don't, in some sense, like, we're not going to have to deal with any kind of special classes. Like, it's, for most graphs, we're going to be able to just give like an answer, which is not an exact answer, but an asymptotic one. And then the bipartite graphs are the kind of issue, but otherwise it's going to be a pretty concrete answer. Okay. So, yeah, so I said we're going to be looking at things asymptotically. So, asymptotically as n goes to infinity. So here's a kind of definition that kind of, captures that. So if I have a graph H, I'm going to define pi of H to be the limit as n goes to infinity of Ex and H over n choose 2. Right? Which is, of course, so like Ex and H is the maximum number of edges you can have in a graph that doesn't have a copy of H on n vertices. And n choose 2 is just the total number of possible edges on n vertices, right? It's the number of edges in the complete graph. So you should think of, for each individual n, that's quite fat. For each individual n, you can think of this as like the maximum percentage or proportion. Let's go with proportion. It sounds more like what a mathematician would say, right? Proportion of edges of, the total possible edges in an H-free graph. H-free meaning it has no subgraph isomorphic to H on n vertices. Okay. And for each n, we can compute this. Well, I can't compute it, but in theory, this ratio exists, and then you can just take the limit as n goes to infinity. But a subtle thing here is like, well, you can take the limit as n goes to infinity as long as the limit exists, right? You can't just take limits of anything. Limits don't always exist. But it turns out in this problem, actually, the limit does exist. So no matter what the graph h is, the limit exists. And so you can define pi of h. And you're going to be asked to prove this in question 4 on assignment 3, which is already released. So, but you're not going to be able. You're not going. No, well, you're not going to be asked to just prove this from the definition. There's a little bit of leading you through it. But yeah, so that question is asking that. Okay. So is the definition of pi h clear? Okay. Yeah. Ooh. I'll go with no. Yeah. But that's, every time somebody gives me a kind of idea I've never thought of, it's always interesting. I then wonder if it can be done in that way. But yeah, that's not the argument I have in mind anyway. Okay. So so this is the Erdestone Theorem. So this is going to be our focus over the next little while. So it says that for every graph h with at least one edge, because graphs with no edges are boring and you can't really avoid them anyway. So for every graph with at least one edge, this pi of h is equal to, let me get it right, the chromatic number of h minus 2 divided by chromatic number of h minus 1. So in the survey from a while ago, everybody who submitted it said they know the chromatic number, but that is surprisingly nice. It's kind of unbelievable that it works for every graph, right? It's just a function of the chromatic number. So remember, the chromatic number is the minimum k, such that you can color the vertices with k colors and adjacent vertices get different colors. So it's just, so if you want to know pi of h, it's just a function of the chromatic number. Now, there is a slight annoying thing here that, like, if the chromatic, this is where bipartite graphs come in. If the chromatic number is 2, then all you learn is that pi of h is 0, which just means that, so maybe I will address this in a minute, but it just means that the extremal number is little o of n squared. And that doesn't tell you very much information. But for all the other graphs that aren't bipartite, it tells you quite a lot of information in terms of the asymptotic as n goes to infinity. So as I've been kind of saying, this is an asymptotic result. It's not an exact result. So it's not giving us the answer. But what it does tell you is that, if I take ex and h for n, which is really large, and let's say, if I fix epsilon greater than 0, let's say epsilon is 1 over 1,000, then if n is very big with respect to epsilon, you do get to say that the extremal number is between chromatic number minus 2 over chromatic number minus 1 minus epsilon and the same thing plus epsilon. So that's what this really implies. Okay. Although the lower bound actually, you can kind of take out the epsilon in the lower bound because we have very good constructions, which I'll talk about in a second. But basically what this theorem implies is what I've got here. That, we can get it up to like a kind of some epsilons. Okay, is that clear? Or any questions about that? So that's just again from the definition of a limit. Okay. So what about a lower bound? So maybe any ideas from the audience? Suppose let's just think about the chromatic number 3 case. So if chromatic number is 3, then so the thing we've got is chi of h minus 2 over chi of h minus 1. So that's equal to a half, in the case where the chromatic number is 3. So what we're looking for is a graph with roughly 1/2 n choose 2 edges, roughly, up to some small tolerance, which doesn't have any copy of h. And all we know about h is its chromatic number. So any ideas? how would I avoid H? And I don't really know anything about H, except for its chromatic number. So H could be a triangle, it could be a 5 cycle, it could be the Peterson graph. How would I avoid all of those things, basically? And I think thinking about the triangle is a bit of a hint. Yeah, exactly. Make it bipartite. Right, so just like with the case of K3, the triangle, if I make it bipartite graph where like I split the vertices in half, roughly in half, whatever, and I put all the edges across. So we've looked at how many edges this has, right? So if I have like about n over 2 here and n over 2 here, I get n squared over 4 edges. And roughly this is like, asymptotically, this is the same as 1/2 n choose 2, because 1/2 n choose 2 is like n times n minus 1 over 4. And yeah, n times n minus 1 is like asymptotically the same thing as n squared. So a complete bipartite graph does have like roughly a proportion 1/2 of all the edges. It actually has a little bit more than a half. So that's sort of related to what I was saying on the previous slide about the lower bound. You actually don't need an epsilon in the lower bound, because yeah, you have this nice construction. Is that clear? So if you want to avoid something of chromatic number 3, just take a complete bipartite graph. And then it's, I guess, probably not a stretch to realize that, the way to generalize this, of course, is to take a complete multipartite graph where the number of parts is the chromatic number of H minus 1. Right? So you've got about n over chi of H minus 1, chromatic number of H minus 1 in each part, and you have this many parts. And is it clear that this can't contain, actually, yeah, we never really explained why it can't contain a graph of chromatic number, well, it can't contain H, but is it clear why it can't? Yeah, exactly. So yeah, in particular, this big graph here, we can color it with chi of H minus 1 colors. And yeah, if it had a copy of H sitting inside of it, then that would give us a coloring of H with chi of H minus 1 colors, but that's a contradiction because of the definition of chi of H. So, okay, there's some messy, so this is kind of hard to read over here, calculation. Maybe I'll do it again, but like how many edges does this thing have, I guess, is we have to kind of check that this has the right number of edges, but it does. So yeah, how to kind of explain this, I'm not sure, but a way to count edges here is you can say, okay, I'm going to pick 2 classes, like 2 of the classes, and I'm going to count all the edges between those classes. So the number of ways to pick 2 classes is chi of H minus 1, choose 2. So that's the number of ways I pick 2 classes. And then after I've chosen, if I count the edges between them, that's going to be n over chi of H minus 1 squared, because that's how many are in each thing. So like if you have a complete bipartite graph of size, a times b, you've got a times b, or sorry, a on one side, b on the other. You have a times b edges if it's complete between them. So this is how many edges you have. Here I'm assuming that n is divisible by chi of H minus 1, but it doesn't make a huge difference. So there's chi of H minus 1 parts because we want to guarantee that there's no copy of H. So if you think about it, if I had chi of H parts, then eventually as the parts get bigger, I'm going to start seeing copies of H because I could just pick the right number of the vertices in each part. But if it's chi of H minus 1 parts, then because H doesn't have a coloring with chi of H minus 1 colors, H can't appear in this graph, basically. Yeah, so it's 1 less than the chromatic number. If you think about like the triangle case, like we wanted 2 parts, right? Not 3 parts. Okay, so then so just kind of, messing around with this calculation a bit. So what does this give us? It's like chi of H minus 1, chi of h minus 2 over 2, but then there's a chi of h minus 1 squared on the bottom, and then there's like an n squared. If you cancel things out and like, you know, draw some squiggly lines, like, so this is approximately a game because n squared is basically the same thing as n times n minus 1. This is like going to give you what we wanted. So chi of h minus 2, chi of h minus 1 times n choose 2, like asymptotically. So you do the cancellation and stuff. So is that clear? Yeah, exactly. Yeah. Yeah, it's at least the value if they were all floors, and it's at most the value where they're all ceilings. And like, yeah, if you think about it, it's not going to make a big difference. Yeah. Okay. So, okay. So, yeah, let's think about how would I prove this? Like, so, okay, so that, what I've shown you so far is a lower bound, right? That's what I've shown you is that, like, this pi of h is at least, actually, maybe I should write that. So this shows that pi of h is at least chi of h minus 2 over chi of h minus 1 because of this example, right? And we want to show that it's equal to this thing. So we want to show that if I take a large graph with like more than or significantly more than like chi of h minus 2 over chi of h minus 1 times n choose 2 edges, then I can find a copy of h, basically. Okay, so we're we're taking a graph which is kind of dense, it has a lot of edges, and we're trying to find a copy of h. That's basically what you can think of for now, the way you can think of it. How am I going to find a copy of h? I mean, like, so this becomes, I mean, it does seem kind of weird that this works for all graphs h, right? Because, you know, the structure of h could be really strange, and so why would this only depend on the chromatic number? If you think about it, though, in order to find a graph h, I mean, all you have to do is find a big, like, complete chi of h partite graph. Okay, so let me explain with an example. So let h be a graph with at least one edge. Let's say that r is chi of h, right? So if r is chi of h, there's some way to color the graph with r colors. So for example, here we've got the Peterson graph. The vertices are colored blue, green, and red. Now if you think about it, if you look at this Peterson graph, right? How many blue vertices are there? There's 3, there's 4 green vertices and 3 red ones. If you think about it, if I could find, so if I take a large graph G, and inside of it I can find a complete tripartite graph where you've got, let's say, well, let's just put 4 vertices in all the parts, for example. So if I can find this graph inside of G, then I can find a Peterson graph, because there's lots of Peterson graphs inside of this one. Because all I have to do is pick, these are my 3 red vertices of the Peterson graph. These are my 3 blue vertices, and these are my 4 green vertices. Okay, and because all of the edges are going between all these parts, like, I definitely can find a Peterson graph because I can just connect things up however I want. Because, we had a proper coloring here, so there's no edges that go from red to red or blue to blue or green to green. So I can find all the edges that I want. Is that clear? So if I let T be the size of the biggest color class, then all I have to find, I don't really have to find the exact specific structure of the Peterson graph. It's enough to find like a complete tripartite graph with big enough parts. Okay, so that's the first kind of simplification. Is that clear? So in general, if the chromatic numbers are, all I have to find is like a complete R-partite graph where the part size is like at least T for some T. Not necessarily, because you might have a graph where the only proper colorings use like the color red on 90% of the vertices. or the only optimum proper colorings. But yeah, I can like kind of mess with this a bit. Like I could make the parts exactly the sizes that you need or whatever. But I can also just say, okay, let's make every part to be the size of the number of vertices of H. And then then I've got way too much room. And I think that's what I do in the notes. It really doesn't matter as long as it's a function of H. Yep. Okay, so here's really the goal then. So we've got a graph. Actually, let me see if oh yeah, so this is what I just said. So it's enough to find these complete R-partite graphs inside of G. Okay, so here's our goal then. So we have a graph G, which has a lot of edges in some sense, where a lot is like in terms of this chromatic number -2 over chromatic number -1 or whatever. And what we want to find is a complete R-partite graph where all the parts have size t, where R and t are like any constants. And the size of n kind of depends on R and t in some sense. So hopefully maybe this statement will make it clearer, although it's a fairly complicated statement. So I'll kind of try to explain it. So, so what we're actually going to prove is that for every R at least 2 and every t at least 1 and every positive epsilon, there exists some n, n naught, that depends on these three numbers, RT and epsilon. So it's so I'm writing it like n naught RT epsilon because like it's a function of RT and epsilon, such that if n is at least n naught of RT and epsilon, then like for every graph G with n vertices and at least R minus 2 over R minus 1 plus epsilon, and choose two edges. So if G is a graph with n vertices and at least this many edges, then it contains a complete R-partite graph with parts of size t. Okay, let that sink in a bit. But yeah, the arguments we've done on the previous couple of slides, by those arguments, what this will imply is that for any h and any epsilon, there's a big enough n for which this holds, where R is the chromatic number of H. Okay, so yeah. So remember before we had this chi of H over chi of H minus 2 over chi minus 1. That has now become R minus 2 over R minus 1 because we're dealing with an R-partite graph that we're trying to find. And so in the Peterson graph case, you could think of T as being 4, right? And R is 3. Okay, and so this is going to, if we can prove this, then it will show that, like what this is going to imply about this pi thing we defined earlier is that pi of H is at most chromatic number, so I'm just writing, well, maybe I'll write H, chromatic number of H minus 2 over chromatic number of H minus 1, right? And then then we'll have a matching upper and lower bound, and then we've proved the theorem. So are there any questions about this? Okay. Yeah, the thing that maybe you might not feel like you're so used to, like, is this whole thing about, making the number of vertices large. That's going to come in later, and there's going to be some sort of a pigeonhole argument, essentially. And I think that's the only place we're going to use that the number of vertices is large. We're going to keep refining something, and then, using pigeonhole, it's going to be, so that's the only place we're going to use that n is large. But that's probably coming like 2 lectures in the future or something. So it's kind of a little bit of a complicated proof. So we're going to take some time on it. So here's the strategy. So here, like at this point, we're assuming G. So G is a graph that has these properties. So it has n, like the number of vertices is large. It's bigger than some bound that we're going to choose later. and it has like the number of edges in G is at least this, right? So this is, whenever I'm talking about G, I'm talking about a graph that has these properties. So what we're going to do, so I mean, in some sense, well, no, I was gonna try to say that in some sense there's a similarity to how we proved Turan's theorem. Because remember Turan's theorem, we took like non-adjacent vertices and we tried to like play with their degrees and stuff like that. It's not quite the same here, but basically our first step is going to be to take this big graph G and refine it to a smaller graph that has a large minimum degree. Okay, so right now we don't know anything about the minimum degree of G. We just know that G has a lot of edges. And we want to like throw away some vertices so that we still have like a large minimum degree. And we don't want to throw away too many vertices because we want to be able to use that n is large. So if we throw away like all but 100 vertices, then we're dealing with 100 vertices and that's no good. We need to like keep the number of vertices large. So we're still going to have, after we throw away some stuff, we want to have a graph that still has omega of n vertices, meaning the number of vertices is still a constant factor of n. Like it's at least c times n for some c, where we're going to choose the c. Okay. And then the second step is going to be to take this G prime that has large minimum degree and build a complete R-partite graph with parts of size t inside of G prime using a kind of greedy approach and using pigeonhole and stuff like that. And we're not going to get to that today. We're mainly going to focus on step one, but that's where we want to get to. Okay, so this is a very high level overview. There's maybe not that much that you necessarily need to understand from this, but this tells us where we're going. So are there any questions about that? Okay, let's make this a little bit more precise by stating a few lemmas. So this is the lemma regarding the first step of the strategy where we take G and we try to find a graph with high minimum degree. So this is called, in the notes, this is lemma 3.16. So it says, let G be a graph with n vertices, and let alpha be the number of edges in G divided by n choose 2. But this is just like the proportion of all possible edges that G has. I'm not sure if that sentence makes sense, but so what the lemma says is that if I take gamma, which is between 0 and alpha, then there's a subgraph of G prime of G. So I'm going to want gamma to be quite small here, by the way. It says that there's a subgraph of G prime of G, where the minimum degree, so little delta here is the minimum degree, in G prime is at least alpha minus gamma times the number of vertices in G prime minus 1. So this means like every vertex in G prime is adjacent to an alpha minus gamma proportion, like to at least an alpha minus gamma proportion of the vertices of G prime. Well, the vertices of G prime apart from itself. So that's why there's a minus 1. And the second condition we're going to want to satisfy is that the number of vertices in G prime is not too small. So here, so it's still at least a constant proportion. So it's, really the second condition is saying that V of G prime is omega of n. As long as so if I'm picking these gammas to be just constants, the alpha and gamma are always going to be constants. So then, yeah, the number of vertices is still a constant multiple of n. Okay, so So this is a kind of technical lemma. Is it clear what it's saying? Okay. So here's another lemma. Maybe I will not say anything about this today because we're not going to prove it. But yeah, so I'll now just talk about the proof of lemma 3.16. So this is the one where we're trying to find a subgraph with high minimum degree. Now, if you think about it, in some sense, if anyone asks you to find a subgraph of high minimum degree, in some sense, there's only one like algorithm to do that. There's like only one strategy. Like, you know, the difficult part comes in analyzing it. But can anyone tell me what do you have to do if you want to make the minimum degree high? I've got a graph. I want to do something to it to kind of increase the minimum degree. I mean, by restricting to a subgraph. Yeah, exactly. You have no choice. You have to do that first, right? Because if I delete an edge, that's not very smart because that's only making my life worse. If I delete a vertex of high degree, that doesn't help. Like I have to delete a vertex of low degree. So that's, yeah, very good observation there. There's nothing else that could possibly help. Okay, maybe you could be clever about which vertices of low degree you delete or something, but yeah, you have to delete one of low degree or else your degree won't go up. Okay, so here's the algorithm. So start with G naught equal to G, or G0 or whatever. And for I at least 1, let Vi be a vertex of Gi minus 1 of minimum degree. So Vi is just an arbitrary vertex of the smallest degree in Gi minus 1. So V1 is the smallest degree in G0, V2 is smallest in G1, and so on. And then I just delete it. So Gi is Gi minus 1 minus the vertex Vi. So when I delete a vertex, I also delete all of the edges, including that vertex, right? So it's, yeah, you delete the vertex and all the outgoing edges. And, well, we're going to stop. So when should we stop? Well, basically, I mean, we want to find a graph with minimum degree, like that satisfies the condition, this inequality here, basically, right? This was the inequality in the lemma. And we want to do this so that the final graph has a lot of vertices. But then the kind of idea is clear, like you keep deleting vertices until you find the first time when this thing is satisfied, and then I stop, right? Because I want to keep as many vertices as possible. So I better stop the first time I see it, the first time I see this happen. So that's when we terminate. And then at this point when we terminate, we let G prime be Gi star. Now, yeah, you have to be careful here when you do this, like when you say I'm going to terminate the first time something happens. Because if you terminate the first time something happens, that only makes sense if you can guarantee that happens eventually, that the condition eventually holds. But in this case, it does hold, like eventually, because, for example, if I delete all the vertices except for one, like if I take G n minus 1, which is like the graph I get after deleting n minus 1 vertices, the minimum degree is obviously 0, and also like the right hand side of this inequality is 0. Okay, so the termination condition is well defined because eventually the inequality will get satisfied, and we just hope that it gets satisfied early, like after only a few steps. Is this clear? So yeah, so this is an observation to remember for later as well. If you're going to get a high minimum degree, you have to delete the vertex of lowest minimum degree. Like you just have to do it. There's no choice. That's going to come up later as well. Okay, any questions? The algorithm clear, the termination condition clear. So all we have to do now is analyze how many vertices are there in Gi star. Okay, or Gi star or G prime, they're kind of, yeah. I define G prime to be Gi star, where I star is the first time that the thing happened. Okay, So how am I going to just check do this? Well, it's actually not that hard to compute the number of, so okay, the number of edges in G0 is just the number of edges in G, right? How many edges are there in G1? So E of, exactly, yeah. And so what I want to do is take that equation and rearrange it. So I think it's called V0, the first one. And so I can rearrange it to say the number of edges in G0 is equal to like G1 plus D of V0. So just kind of rearranging things a bit, but that's exactly the right thing. That's what I was asking for. So then in general, if I look at the number of edges in GI minus 1, it's the same as GI plus the degree of VI. So VI is the vertex, I think. No, yes. VI is the vertex you delete from GI minus 1. So this is, all I'm doing is, taking this equation for general I and rearranging. Okay, maybe it is. Yeah. Good. Yes. Thank you. So this should be an I minus 1. Yeah. I think that's going to make my next equation make more sense. So then the number of edges in G, which is G0, right? G0 is G, is the edges in GI star. So I'm just kind of applying this thing over and over, right? So this is like this. You can kind of see this kind of inductively, right? Because if I looked at the, I star minus 1, it's GI star plus degree of VI star minus 1. And then you look at minus 2 and minus 3, and you can see that it just adds up these degrees here in some sense. Okay. And now we get to use the fact that we get to use the minimality of I star. We get to say that because I star was the first time we terminated, we can say that these degrees must have been small. Okay. Because otherwise we would have terminated earlier. So here's the algebra. So here in the first line here, what I'm doing is I'm just using, so we've got 1 minute left, perfect amount of time, maybe slightly low. So here I'm using the equality I got from the last slide, but I'm plugging in the fact that DI, the degree of VJ is small. So it's the degree of VJ is smaller than this. Okay. Otherwise, I would have terminated at the jth step instead of at the I star step. Or, yeah. And this, the number of vertices in GJ is just n minus j minus 1, I think. Yeah, because in the case j is 0. Oh, sorry. The number of vertices is n minus j, and then I've got a minus 1 here that goes with that one. Okay. So here, this is just now some calculations. I should probably let you go. But, this is a trivial upper bound on the number of edges in GI star. It's just how many vertices choose 2. And this thing is just a sum of consecutive numbers, right? So I've got the alpha minus gamma here. And then I've got a sum of consecutive numbers going from n minus I star up to n minus 1. You'll probably remember how to, if you add up from 1 up to n, that's n plus 1 over 2. That's a Math 222 thing, or I don't know. So you could just write this as n choose 2 minus n choose I star. Maybe I'll just finish this off on the next lecture. So before the break, we're in the middle of a proof, which maybe is not the best time to have a break, but oh well. So do you remember what we were proving? We were proving this Erdestone Theorem, which says, so this is about the Turenne, or the extremal number of a general graph H. So remember we had this definition. So this is a definition of this pi of H. So it's the limit of the extremal number of H on n vertices, or the nth extremal number or something, divided by n choose 2. as n goes to infinity. The extremal number was the maximum number of edges in graph on n vertices with no h, no copy of h. And the theorem we were trying to prove is that this limit is just equal to this. So this is, so from this from this equality onwards, that's the theorem, right? This is the Erdestone Theorem. Some people call it the Erdős-Simonovitz theorem. Yeah. So remember we had a sort of, so the way we wanted to prove this was we took a graph with more than this number of edges. So more than, or sorry, there should not be an n choose 2 here. Right. So we took a graph with more than like chi minus 2 over chi minus 1, where chi is chi of h. So this plus epsilon, let's say, n choose 2 edges. And we had this kind of two-step idea. So what we wanted to do first was say, okay, I could take this graph and I can find a subgraph which has large minimum degree. And then the second step was inside of that graph of large minimum degree, I want to find a complete multipartite graph where the number of parts is the chromatic number of h and where the parts can be as big as I want. Okay, let's not worry about the whole big picture right now, but where I was at the end of the last lecture was proving this lemma, that if the number of edges in G is, let's say, alpha times n choose 2 for some real number alpha, or I guess it has to be a rational number alpha, then for any gamma between 0 and alpha, G has a subgraph G prime where the minimum degree is like at least alpha minus gamma times the number of vertices in G prime minus 1. And the number of vertices is not too small. Okay, so we were actually almost at the end of proving this last time. Okay. And one thing you might remember from last time is that to prove this, we were basically analyzing a very simple algorithm, which is kind of like the only algorithm that could possibly ever work for this. Right? So you start with a graph and you want to get a subgraph with large minimum degree. Well, how am I going to do that? Like, pretty much the only thing you can possibly do is delete a vertex of small degree. Because if you don't delete a vertex of small degree, then your degree won't go up, if that makes sense. Or basically a vertex of smallest degree is the best thing to delete, right? And we're just analyzing this algorithm and saying, okay, we stop at the first time we get a subgraph which satisfies this condition. Okay, so we just keep deleting the vertex of smallest degree until this holds. And what we wanted to show is that at the final step, the graph G prime has at least this many vertices. So some weird function of gamma and alpha times n. The square root of blah, blah, blah times n vertices. Which in other words is the same as saying we want to show that the number of vertices you delete is not too big. Okay, this is where we were in the proof. This is not... So basically we were at a point where everything that's left to do is just a bit of algebra. So we got this inequality here by looking at... So I start with my original graph. I delete the vertex of smallest degree. So first of all, I start with my original graph. If G satisfies the condition we wanted, I would just stop. If not, I delete the smallest degree vertex. And then if the next graph satisfies it, then I stop. If it doesn't, then I delete the smallest degree vertex. And by doing this, we were able to say that, so I star is the number of steps, the number of vertices you delete before you stop. And by just kind of analyzing this process, we were able to say that the number of edges in G is at most this value, which is, n minus I star choose 2 plus alpha minus gamma n choose 2 minus n minus I star choose 2. And this was just a basic counting counting how many edges you delete. Okay, right? So in each step, you delete a certain number of edges, which is based on the fact that the minimum degree condition didn't hold. And yeah, if you kind of keep track of, you do the bookkeeping, then you get this bound. Yeah, this is not very enlightening, to be honest. So let's maybe go through this sort of quickly. So this is just algebra. All I'm doing here is I'm taking, so I have this equality here. So this is by hypothesis that the number of edges in G is alpha n choose 2. That was my assumption in the lemma. So you can kind of solve this. Like you've got you've got things that have a n choose 2. So I ignore the E of G here. I just take alpha n choose 2 less than the stuff on the right side. You've got stuff with n choose 2s, and you've got stuff that has n minus I star choose 2s. And you can kind of collect this up, right? And you end up with this because, yeah, when I bring this over, you just have a gamma. When I put this stuff together, you have 1 minus alpha plus gamma in front of this. Yeah, and this really, again, isn't very enlightening. But like, basically, I kind of want to solve for, basically the last step is to solve for I star, which is kind of a pain because, so one annoying thing about n choose 2 is that it's not the same as n squared over 2. I mean, n choose 2 is like n times n minus 1 over 2, which is almost the same thing as n squared over 2. This n minus I star is kind of like n minus I star squared over 2, but it's not. It's like something like this, right? But if this was really n squared over 2, and if this really was n minus I squared over 2, then it'd be pretty easy to solve for I star, right? You just, I don't know, multiply both sides by 2 maybe, take square roots, do some dividing, and you'd be done, right? And you subtract and whatever. So basically this last slide is, well, I believe, yeah, this is, you can basically do that. Except on the right side, you have to replace n choose 2 with n minus 1 squared, and on the other side, replace n minus I with n minus I squared, or I star squared. Anyway, if you fiddle around with the algebra, you'll see that you can basically kind of solve, like, so here I've replaced the left-hand side with something smaller. So I got rid of the over 2 thing. I replaced the right-hand side with something a little bit bigger. Anyway, you get that I star is, when you do all the solving, it's less than this, which tells you that n minus I star is bigger than what we wanted, which is the number of vertices in Gi star. So that's the number of vertices when the algorithm stops. Okay, so that, yeah. Yeah, it's a good question. So the question was, yeah, will it ever stop before that time? And the answer is yes, because maybe the graph might have been like if G is, let's say, alpha n minus 1 regular. So G has alpha n choose 2 edges. I think is this the right number here? Yeah, I think so. So if G was alpha n minus 1 regular, then actually the algorithm would stop before it does anything. It wouldn't delete any vertex because the minimum degree is already like at least alpha minus gamma. So gamma was something which is bigger than 0 times the number of vertices minus 1. That was the condition we were trying to satisfy. So it could have been satisfied right from the beginning, in which case we would just stop immediately. It could be satisfied after only a few steps. And but this just guarantees that at some point it'll be satisfied, and when it's satisfied, you haven't deleted too many vertices. But that's a good question. So yeah, the algorithm may stop earlier. Any other questions? Yeah. Okay. So actually that first lemma, in some sense, we haven't used anything about G being H-free, like that G doesn't have a copy of H. That first lemma you should kind of recognize, like that has nothing to do with the graph H, and it has nothing to do with this problem in some sense. Like for any graph, I can always find a subgraph with high minimum degree. That's basically what the first lemma says. The second lemma now is more related to the problem we're dealing with. So do you remember there was this example of like the Peterson graph, right? I was saying, and that was meant to illustrate the fact that, so if I want to find a copy of H in a graph G, well, and let's say H has chromatic number R. So maybe R is 3. So H has chromatic number 3, let's say. To find a copy of H, it's sufficient to find a complete tripartite graph where the parts are very big, right? Because if I can find a complete tripartite graph where each part is very large, then I can find H by just basically taking the 3 different color classes and putting them in the 3 different partite sets of the tripartite graph, right? So basically, remember, everything boils down to trying to find copies of complete R-partite graphs where the parts are really large. Okay, and this lemma now tells me that as long as the minimum degree in the graph is large, I can always do that. And the number of vertices is sufficiently large as well. Okay, so let's explain what this lemma says. It's kind of a technical one. So we've got R at least 2, T is at least 1, epsilon is positive. So it's a kind of asymptotic result. So here we're going to deal with graphs with a large number of vertices. And you'll see where, well, I'll try to explain where the largeness of n matters, because basically it's going to come in like a sort of pigeonhole argument that you're going to need to have a lot of vertices to make it work. So it says that there exists some number, let's say n sub 1, rt epsilon. So it's a function. So this is a function of rt and epsilon, such that if G is a graph with at least that many vertices, where the minimum degree in G is at least this much, which is kind of like so this r minus 2 over r minus 1, this is related to, in the Erdestone Theorem, the chi of h minus 2 over chi of h minus 1 that we saw in that theorem. Okay. Because you should think of R as being the chromatic number of some graph H, and we're trying to find a complete R-partite graph. So if G has a lot of vertices as a function of RT and epsilon, and if the minimum degree is at least this quantity here, so R minus 2 over R minus 1 plus epsilon times the number of vertices minus 1, then G contains a complete R-partite graph where the parts have size T. And a kind of consequence of this, which is what we really care about here, is that, so that implies that G contains every graph H with chromatic number R, and let's say the number of vertices in H at most T. Okay. And then after we prove this, we'll see that these two lemmas, when you put them together, actually imply the Erdestone Theorem. Yep. Oh, sorry, I'm saying here the number of vertices in H is at most T. And this is actually a bit wasteful, but so I guess what I'm saying is suppose G does contain, so if I can find an R-partite graph, let's say 3-partite, just because 3 is a nice number, where all the parts have size T, then so it's complete tripartite, then I claim I can find every, any graph I want that has chromatic number 3 and it has at most T vertices, because I look at the red vertice, so I look at a coloring with 3 colors, I look at the red vertices, I've got enough space that I can put all the red vertices here, the red vertices of H. I look at the green vertices, let's say, I've got enough space I can put them here. And let's say I've got yellow vertices. I've got enough space I can put them here. Does that make sense? Yeah. Yeah, totally. Yeah, because all the parts will have at least one vertex. Yeah, it's almost tempting to say you could do T over R, but that's not quite true because, yeah, the color classes might have different sizes. But yeah, it's something like what you said, T minus R plus 1 would work. Yep. Okay. Any other questions? Okay. So, so now we're going to try to prove this lemma. Okay. Oh, okay. Let's get into the proof. So, okay. So our assumption is that G has minimum degree at least this, right? This was what we had in the statement, and has a large number of vertices. Where I'm not gonna, for the time being, I'm not gonna tell you how large it has to be, but hopefully that'll become clear later in the proof. And what we're looking for is we're trying to find an R-partite graph inside of G where all the parts have size t, size at least t, or let's just say size equal to t. So the way we're going to do this is kind of greedily build it kind of part by part, right? But we have to be a little bit careful with how we do this. I mean, imagine I'm trying to do this. I have G. I'm trying to build the first part, the first first part of my complete R-partite graph with T vertices in every part. I mean, it's tempting to just say, okay, I pick T vertices to form the first part. I mean, if I pick any old vertices, let's say T is 5, that should be good, right? But then I could run into problems when I try to build the second part, right? I want to find 5 vertices which have, which are all adjacent, to all of these 5 vertices that I took for the first part, right? And then I want to find a third part, let's say if R is at least 3. So I want another 5 vertices adjacent to all of the stuff I've seen before. And then another 5, if R is at least 4, that's adjacent to everything I've seen before that. And if you think about this, this isn't maybe a great idea, because the first part, in some sense, the first part is the easiest one to build, right? Because I can build it as big as I want in some sense. The second part is harder to build because I have to have everybody adjacent to everything before. But it's kind of easier than the third part is going to be in some sense. So here's the strategy is actually going to be to build larger parts in the beginning and then throw some of them away as we go. Because basically, let's say suppose I successfully build, 2 parts of the complete multipartite graph. Well, maybe whenever I pick 5 other vertices, maybe one of them misses, doesn't have an edge to the first one doesn't have an edge to the second one doesn't have an edge to the third one, and so on. And I want to be able to kind of throw some old vertices away so that I can build my next part. I don't know if that was helpful at all. Probably it wasn't. But let's go into the formal details, and then hopefully maybe it becomes a little bit clearer. Yeah, this is where the pigeonhole is going to come in. Basically, I want to say that, there's a lot of, so when I try to build, let's say the 4th part or something, I want to find a lot of vertices which have the same neighborhood into my previous parts, and where that neighborhood is big. Okay, and if I take them all with the same, or the same neighborhood, or at least containing the same set of vertices or something, that's where the pigeonhole comes in. Okay, let's do this properly though. So I'm going to define some numbers. So the numbers are T sub S, where S is between 1 and R. So I start by defining TR to be T. Okay. TR, so this T is the size I want the parts to be at the end when I have R parts. And then I define for each S between 1 and R minus 1, I recursively define TS to be 2 times TS plus 1 over epsilon. So this is not a 3, it's backwards, right? So this is an epsilon, and this is the same epsilon that we have here. So that epsilon is that epsilon. So basically every time, so TR is the smallest one, TR minus 1, I times by 2 and I divide by epsilon, so it's, it's kind of quite a bit bigger than TR, then so on and so forth, all the way down to 1. So here's what we're actually going to prove. So our claim is that for every S between 1 and R, G contains a complete S-partite graph where the parts have size TS. Okay, and we're going to do this by induction on S in some sense. Okay, so is it clear why this will finish the proof? Exactly, yeah, because TR is T. So therefore, if I apply this, if I apply this with S equals R, then you get complete, we get what we want, a complete R-partite graph with parts of size T. Okay, so this is kind of what I meant. So like for the first part, we're going to make it much bigger than we need. And then when we have two parts, it's going to be still bigger than we need, but a little bit smaller than before. And it kind of shrinks and shrinks and shrinks. Like the part size shrinks and shrinks and shrinks. And in the end, you've got what you need, which is T. Okay, so induction on S. The case S equals 1 is kind of easy. So, right, just pick any T1 vertices, right? And if I just take any vertices, so I don't really, they don't have to be an independent set or anything. They can just be any T1 vertices. And that's like a complete one-partite graph. Okay. Here's a subtle thing, right? Oop, that's not how you spell subtle. This tells you that we need the number of vertices in G to be at least T1, which is kind of like 2 over epsilon to the R, maybe R minus 1 times T or something. So already we have to have the number of vertices be large in order to even do the first step. Okay. I mean, it's not, so this asymptotic maybe isn't, I don't really mean asymptotic here, but it's sort of like kind of like this. Okay, so the first step, we just take any T1 vertices of G, which we can do because the number of vertices in G is large. Okay, so here's the interesting step, which is the kind of the inductive step. So, and this is where we're going to use pigeonhole. So, right, so everything up here is just repeated from before. So here's where we should be going next. So, yeah. We kind of have initialized it, but so the way this was defined was kind of weird. It was kind of backwards. Like we defined TR to be T. Let's see. Make sure that I did initialize it. And then for each S, we defined TS to be in terms of TS plus 1. Yeah. So that'll go all the way down to 1. And basically, I mean, so I had to put these ceilings in because of integers are annoying, but basically when you go from TS plus 1 to TS, what you do is kind of multiply by 2 over epsilon. So that's where I got this, like the fact that T1 is roughly, is kind of like 2 over epsilon to the R minus 1 times T. Okay, so now we're doing the inductive step. So so what do we want to, so we've got S, which is between 2 and R. And we can already assume, so we can assume the previous case, right? The S minus 1 case. So we can find a complete S minus 1 partite graph where all the parts have size like T sub S minus 1. So I can find these disjoint sets B1 up to BS plus or S minus 1. So it's a complete S minus 1 partite graph such that the size of BI is T sub S minus 1. Okay, so that's where I get this picture in the corner. So this is what these things look like, where each of these sets have size at least TS minus 1. Okay, so we want to build the next set, the next part of the complete so S partite graph. And so what we want to do is we want to find TS vertices. So those are going to form the S part of the complete S partite graph, the Sth part. I'm trying to say STH, like Sth, which is quite hard to say. So what we want is like a bunch of a vertex or a bunch of vertices where there's a kind of common. So Ts, by the way, is smaller than Ts minus 1. So Ts is like epsilon over 2 times Ts minus 1, give or take. So there's these ceilings that kind of messed it up, but give or take, it's like epsilon over 2 times that. So I want to find like an epsilon over 2, proportion of each of these. Well, so I want to find Ts vertices in each of these things. And I want to find Ts vertices that are not in any of these sets. And I want all of these vertices in this new set to be adjacent to all of these kind of special vertices in all of the parts. Okay. And if I can find that, then that's my S partite graph, if that makes any sense. And notice, like, it's not good enough to find Ts vertices which have at least Ts neighbors in all the sets. They have to be the same set. They have to be all adjacent to the same set of Ts vertices, right? And to actually find the complete multipartite graph, what I would do is I would throw away all of this stuff, right? Maybe that wasn't clear. I'm not sure. And I'd be left with with what I wanted. Is this clear? What we're looking to find? Okay. Yeah, which is it seems like a weird thing that it goes backwards like that, but yeah. Basically, Ts is, so epsilon is some small number, right? And Ts is about, like, roughly epsilon over 2 times Ts minus 1, so it's definitely small. Ts is definitely smaller than Ts minus 1. And it's like quite a lot smaller. It depends on epsilon. Yeah. Okay. So let's look for this set of vertices. So I define B to be the union of the S minus 1 parts. So this is, just the union of the vertices. I let U be the vertices of G minus B. So U kind of stands for unused, right? So far, those vertices are unused. And I want to basically use them. And I let W be the set of all vertices in U where the neighborhood of V, so all unused vertices, so all vertices in U, V in U, where the number of neighbors of V in BI is at least Ts for all I. So I between 1 and whatever it should be, S minus 1. So the vertices in W are kind of my good vertices. Like these are the vertices which have enough neighbors in all of the sets so that they could, in theory, be part of the new part of the complete multipartite graph. But we still, like I said, have to find a lot of them which have the same neighborhood. But yeah, at least these ones have good enough, like large enough neighborhood in those sets. So W is not really in the picture. So it's part of the like unused vertices, which are kind of over here, let's say. So these are the vertices that are not in B. And a vertex in W is one that's over here. Yes, that's a good question. How do we know we have unused vertices? Well, you can assume, because we're assuming that the number of vertices in G is very large. And the number of vertices in B is only S minus 1 times Ts minus 1, which is a kind of finite constant number. So there's always going to be some unused vertices over here. And W is the set of unused vertices, which have a lot of neighbors in all of the BI sets. So W is some subset of U, which is the vertices that are not in B. W, let's say. But that's a good question. Yeah. So it's outside of these, what we've built so far. And we're going to try to use some of that stuff to build the next step. So we want to show that W is enormous. In particular, we want to show it's bigger than this. And I'll explain why, I think, later on. Okay. So yeah, we want to show that W is very large. And the way we're going to do that is with some kind of double counting, where we count, essentially what we're going to do is count the edges from U to B in two different ways. So Okay, so here I've got B, which is the stuff I built so far. Maybe B can mean built. I've got U, which is the unused vertices, which kind of split into two parts, which are W and U minus W. W are the good ones that have lots of neighbors. U minus W are the kind of crap ones, rubbish ones. If V is in U minus W, how many non-neighbors does it have in B? So it has to have at least, it's definitely got at least S minus 1 non-neighbors in B, but it actually has a lot more. Because if V is over here in U minus W, the number of neighbors it has here is less than, so if this black circle is the neighbors of V in here, then it's less than Ts. But that only has to happen for one of the, actually, yeah, so S minus 1 maybe is not quite correct. It just has to have less than Ts neighbors in some part. So it has at least Ts minus 1 minus Ts non-neighbors in B, because there's some part for which it has a small number of neighbors. Right? V might be actually adjacent to everything everywhere else, but there's some class, some part where he has a small number of neighbors. So he has a large number of non-neighbors. And remember that Ts minus 1 is, was it at least? Yeah, is at least 2 over epsilon Ts. By how we defined it, it was actually equal to the ceiling of 2 over epsilon Ts. So this whole thing is at least 1 minus epsilon over 2 Ts minus 1. So that's just coming from this. So if I count the number of non-edges from U to W, it's at least, so if I do it vertex by vertex, it's like for every one I count at least, so this is the number of vertices in U minus W. For every such vertex, I count at least this many non-edges. And how big is U minus W? Well, it's just the same thing as number of vertices minus B minus W, because U is just all the vertices minus B, and W is a subset of U. So this is just rewriting the size of U minus W. Okay. Is this too quick? I think everything here kind of can be easily verified, but yeah, really the key was just this. Okay, so I said I was going to kind of double count things. So here's the another way of counting. So remember, we haven't even used anything about the minimum degree, but the minimum degree in G is at least this quantity here from the assumption, the hypotheses. So each vertex is only adjacent to, at most, 1 minus this. So if you think about it, it's 1 over r minus 1 minus epsilon times number of vertices minus 1 non-edges in total. So this comes from like taking the thing in here, taking 1 minus the thing in here. Right, because the minimum degree is large. So how many non-edges are there from U to B? Well, it's at most what I would get from just going over all the vertices in B and adding up all the non-edges in the whole universe that are incident to that vertex, which is going to be at most the size of B times 1 over r minus 1 minus epsilon times the number of vertices in G minus 1. Which, let's see, is at most, so what I've written here is that the size of B is at most Ts minus 1 times S minus 1. So that's, in fact, it's equal to that, right? Every part has size T sub S minus 1, and there's S minus 1 parts. And S is at most R, so so this is then at most, let's see, 1 minus epsilon r minus 1 times Ts minus 1, number of vertices in G minus 1. Hopefully that's what I've got written on the next slide. Let's see. Oh my gosh, it is. Can't believe it. Okay, it's almost the same thing I've got written on the next slide, except I threw something away. Okay. This is how the double counting works. We showed that the number of non-edges from u minus w to b is at least something, and that it's at most something. So we can kind of write that, those things together. Like we can say, so the number of non-edges was at least this on the left side. We proved that 2 slides ago, and it's at most this, which we proved in the last slide. So therefore that has, the left-hand side is less than the right-hand side, or at most the right-hand side. And now we solve for w, right? So the algebra here is just solving for w. Okay, so nothing terribly interesting is going on here, right? I just kind of cancel these because you can, because they're multiplied to everything. I just move the w over to the other side, move the other junk to the other side. And what we can say is that the size of w is at least whatever I've got on the right-hand side. And now, remember, the number of vertices in G is at least some n1, which depends on r, t, and epsilon. And I could make that as big as I want as a function of r, t, and epsilon. Okay, and this is also just a function of r and t. Okay, there is an s there, but even with that, it's still bounded by a function of r and t. So in particular, if I just take this n1 thing as large enough, I can get that the size of w is bigger than this thing. T sub s minus 1, choose ts to the s minus 1 times ts minus 1. Okay, so as long as the number of vertices is big, w will be at least this big. Okay, I know I'm out of time, but I think the last thing I just wanted to say is a quick pigeonhole thing. So why does this finish everything off? So okay, here's the counting thing. Let's just forget about Erdestone for a second. How many ways are there to choose a subset of bi of size ts for all I? And remember that the size of bi is equal to ts minus 1. How many ways can I choose it? Yeah, for each of them, I'm going to choose a set of size ts. How many ways can I do that? Yeah, so individually, for a given, like for b1, let's say, you've got ts minus 1 choose ts. And if I'm going to do that for every single one sequentially, and I can choose, different subsets of each of them, and I'm kind of choosing like a kind of vector of subsets in some sense, one for each I, then I get this to the power s minus 1. Okay, and basically so what we proved is that w has size at least this, strictly greater, so the greater is actually important here. Since w is greater than that, by pigeonhole, there must exist t sub s vertices in w, which are all adjacent to the same set of ts vertices in all the bi's. Okay. I don't think I need anything about it being. I don't think I even need anything about it being greater than or equal to. If it was 1, I guess. Are you kind of concerned about this or something? Yeah, I think it'd be fine. I think it works out to be fine. Right, so I can find ts different vertices in w, which are adjacent to the same set of ts vertices in each of the things. I make that my sth part of the bipartition, or the not bipartition, but multipartite graph. Okay, there might be some. If you are concerned, so the one thing to kind of be concerned about here potentially is that I define this to have. This is not quite right. So this is. Oh, sorry. So this is supposed to be for all I. That this is at least ts, so you might think, oh, what if it's bigger than ts? But actually, you could just remove some edges whenever it's bigger than ts, and it'd still be fine.